So hi everyone, my name is Matt.
My name is Kumi.
I'm Audrey.
I'm Aidyn.
I'm Ruby.
And we are Team 13. Our project was to build a computer interfaced graphical impedance analyzer for Schlumberger-Doll research, and our customer was Simone, Musso. A little background on the project is that cement is the main material used in sealing the extraction pipe in oil wells. If it becomes deteriorated and cracks or falls apart, you have a big oil disaster and a spill, hence BP and a couple years ago in the Gulf of Mexico. So with our analyzer, the hope is to better develop models of a smart cement that Schlumberger is currently developing, which has an electrical tracer embedded into the cement. When the cement becomes stressed, through this tracer, the characteristic impedance will go under a drastic and predictable change. By comparing the change of a stressed model to a known good model for the impedance of a cement sample, you can then verify if the oil well, for instance, is no longer safe to use. So the design overview is it's an impedance analyzer that sweeps from 25 Hertz to 200 kilohertz. The signal is created by an onboard DDS chip, which is powered by a microprocessor. It outputs a constant RMS voltage, but the frequency is user controlled. This is how we do our sweeping. This then goes into an output stage where we can then select the output voltage the user would like to send through the sample. After this output stage, it goes into the output loop of our analyzer, which has the load and all the other measurement circuitry. This includes current measurement, voltage measurement, and phase measurement, leading and lagging, which do all the send back data to the processor to do all the onboard calculations of impedance and phase.
So my name is Kumiszhan. I'm one of the hardware developers in our project. My responsibilities include designing signal output voltage control stage. I also worked on power supply with Aidyn and Matt and helped with PCB. So for the amplifier and voltage driving stage, we have 7 stages of amplification. 6 of them could be calibrated for to 0.1, 0.2, 0.3, 0.5, 0.75, and 1 volt RMS values. And the last stage is the user adjustable, which allows the user to select any voltage value between 0.1 volt to 2 volt RMS. I also used class AB push-pull output driver for 2% load regulation. For our power supply, we used 120 volt AC to 12 volt AC 2 ampere rated power adapter. There are 4 power rails in our power supply, which are plus minus 10 volts, 5 volts, and 3.3 volts. I also helped with to edit PCB schematics and generate Gerber files.
So my main task for the project was developing the measurement stages. These are differential measurements of load current and load voltage. For load voltage, we can measure directly across whatever load is put in the output loop of the analyzer. For current, we're using a sense resistor setup and measuring the voltage drop across a known sense resistor and scaling it accordingly for ADC measurement, and then back calculating the current based on that known resistor value. It's all auto-ranging in order to maximize the measurement range. The scaling for, say, 1 microamp of current is a lot different than 1 milliamp. So in order to measure that with our ADCs, we have a scaling algorithm which implements automatically. And in order to ensure that there's no discontinuity in the measurement, all the gains of the stages can be calibrated precisely using trim pots, so that as you're sweeping, say, a capacitor, which goes from essentially open circuit to short circuit at high frequencies, when the gain of the stages switches, there's no discontinuity. I also designed the enclosure, which are out on the table, and I aided in power supply and phase sensing design.
I did the software and microprocessor programming for this. The software consists of a command line interface written in Python, which takes user commands and transmits them serially to the microprocessor, which is the TI-C2000 Piccolo Launchpad microcontroller unit. This parses the command string and sets the hardware controls, and also transmits the frequency to the function generator chip. As the program is running and collecting samples, it receives the input into the ADCs and does the back calculation to find the load current and load voltage as well as changing the gain stages if required, if the impedance is either too high or too low. Then it returns this data to the computer serially, writes it to a text file, and allows it to be plotted via user-specified parameters.
Hi, I'm Aidyn. My role in this project is to generate a signal generator and a power supply. Signal generator, we used direct digital synthesizer because it's very precise with increment of the frequency, and it also gives a very accurate sine wave. By inputting the digital 8-bit signal from the microprocessor to the digital synthesizer chip, we get a very precise output of the sine wave with a 1 volt peak-to-peak voltage and with the offset 0.5. Also, we're going to sweep it from 25 Hz up to 200 kilohertz, even though it can go from 0 to 70 megahertz. I also checked for the ripple voltages of the power supply, that is noise, and we get it is very accurate and very noiseless power supply. And I also helped in PCB in debugging it.
So hi, I'm Rubing, and I did the phase measurement and the PCB design for the cement impedance analyzer. So for the phase measurement, it basically measures the phase difference between the input and the load signal. That is the signal that comes from the output of the voltage control stage and the signal that goes through the load, in this case, which is cement. And the phase difference, it goes from 0 degrees to 180 degrees. 0 degrees means it's in phase, the two waves are over each other, and 180 degrees, which means that the phase is completely out of phase or anti-symmetric. Now, there's also positive and negative phase because either one signal can be leading or lagging versus the other one, and that lead and lag detection was used was done through logic with the flip-flops. The phase does also vary with frequency, and from this you can actually identify the properties of the load, whether it be inductive, resistive, capacitive, or a mix of many of them. So I'm also responsible for the PCB, and the PCB was separated into two components. There's a power PCB and a measurement PCB. The power just comes with the power supply, and the measurement PCB includes all the voltage, current measurement, and phase measurement, and the C2000 microprocessor. I also did the PCB layout and debugging, and I aided in creating the Gerber files. So now we have a video that's going to demonstrate how this works.
Here's our full analyzing setup using a computer interface and an oscilloscope to monitor voltages. We're using a cement sample donated from Schlumberger-Doll. The user now has to enter a set of parameters for the test. We are selecting a frequency sweep of 25 Hz to 200 kHz. The output voltage is going to be 0.3 volts RMS. The number of steps 250. And now the user is prompted for the file name in order to save the text file. Your warning shows that our analyzer is working. Here we are using the monitoring feature of our analyzer to monitor both the generator voltage and output voltage of the cement. We are watching a frequency sweep and phase shift. After the analyzer has finished running, the user will be prompted for plotting features. Here the user is selecting impedance versus frequency and phase versus frequency subplots. Now the plots are displayed.
So that was our video. Now the example, our system is designed to work well for with different kinds of loads, such as resistive, capacitive, and inductive. And the two figures on the right that you see are the plots of impedance versus frequency for the inductor and the capacitor. And we back calculated the inductor and capacitor values, and they were in about around 10% accuracy range. And the figure on the left is the impedance versus frequency plot for the cement sample. And based on our accuracy results for the capacitor, resistor, and inductor, we can conclude that impedance measurements for the cement should be also accurate. Closing remarks. So as we calculated, the impedance error is on average between 2 to 15% of error, and it meets the design goal of 15 maximum error of our project. The hardware works reliably and consistently, and we really feel that our project was a success and will meet all the requirements of our customer. And we would like also to thank our customer Simone Musso from Schlumberger-Doll Research Company, Professor Pisano, Professor Kia, Professor Klepson, for making it possible for us to work on this project and complete it. Thank you. We are now ready for questions.
Yes.
So you measured just a little cylinder of concrete, as I stated, but if you were going to measure the concrete in an actual oil well, how do you get the signal down below the concrete so you can measure the impedance for it, whatever?
Well, that's a different problem.
Yeah.
Like our goal for this project was it's for the lab. It's for developing the models of this cement because they're playing with the mixture, the ratio of this electrical tracer versus the volume of cement. So they want to determine models to determine if, when the cement's been crushed, if you have a dramatic enough impedance change that's accurately reflected and it can be determined that the cement is no longer usable.
So they're not going to use this in an actual oil
Well,
well.
eventually the goal is, but they want to, before digging an oil well and pouring cement, they want to develop models first. That's the goal. Yeah, right.
Are there any existing technologies that do something like this? And
Yeah.
How does it compare?
So there are a lot of graphing impedance analyzers on the market, but as you might be or may not be aware of, they're $30,000 or $40,000. The big benefit of our system is it's significantly cheaper and may not have the accuracy of those, but for running lots of samples quickly, it should be a very beneficial tool. And then if they find a model that they do, in fact, want to pursue further, they can then use a more accurate analyzer. But it should save time.
Also, does the error increase as you increase the frequency, or is it a steady error?
It does a little bit. The error is kind of hard to correlate because we also have selectable output voltages. So it also varies with output voltage. Some of the, a really high impedance is really hard to detect with a small RMS output voltage because the current is just so low. So in our user manual, we recommend that you use the highest permissible output voltage for your load. Yeah, it's measuring impedance absolutely, so there's no reason it should not work under any load stick between the output terminals of the device.
Right, thank you.